All right. Hello, everyone. Welcome to Penn State CTSI BERD seminar series. The BERD stands for Biostatistics, Epidemiology and Research Design. For this semester, for 2024, the BERD seminar series is co-hosted by me and two colleagues of mine, Dr. Lan Kong and Dr. Terry Murphy. Dr. Murphy is actually the speaker for today, and my name is Jay Zhu. We are all faculty members in the Department of Public Health Sciences at Penn State. On this page, you can actually see the list of the topics for this fall semester. And we already passed the midpoint of this semester. And if you are interested in the last two topics, I encourage you to go to this website to register. And here, this is a list of some general logistics for this Zoom webinar. The Zoom session is being recorded automatically. And for the attendees, please mute your microphone when our speaker is giving a lecture. If you have questions, please do feel free to submit your question using the chat box of the Zoom during the lecture. And at the end, you may use your microphone or camera in the Q&A session. If you registered for this seminar, you will receive the slides, the recording link, and the seminar feedback survey afterwards. And today, we're actually very happy to have Dr. Terry Murphy to give us some introduction to missing data methods. Dr. Murphy joined Penn State in 2022 as a professor of biostatistics at the Penn State College of Medicine. Previously, he worked in the Yale program on aging and directed the Biostats core of the Yale Claudie D. Pepper Older Americans Independence Center. Most of his work has focused on longitudinal analysis of observational data, and his research interests include a wide variety of analytical approaches, such as spatial methods, complex survey design, Bayesian methods, and joint methods. Dr. Murphy has published more than 150 peer-reviewed papers and made significant contributions to the development and application of statistics methods for geriatrics research. His current interest is in longitudinal analysis that use structural equation models to address issues such as reverse causality and measurement error in a multivariate framework. It's very nice to have you, Terry. Without further ado, the floor is yours. Let me stop sharing and you may get started.
Thank you, Jay, for your very kind introduction. I'm Terry Murphy. I'm going to call up my slides now. And I thank you all for showing up just after lunch to listen to a statistical lecture. I've advised people to take caffeine beforehand, but I will do my best to keep this somewhat dry subject moving along. So the name of my talk, A Gentle Introduction to Missing Data Methods. And as Jay said, this is part of our BERD fall seminar. Here's an outline of the talk. Why is missing data a problem? And we're going to talk about 3 types of missing data that were first defined by Don Rubin that provided a context in which to talk about this, like I said earlier, somewhat abstract idea. We're also going to discuss 3 approaches. There are more approaches than the 3 I'm going to talk about, but because we don't have that much time, I'm going to focus on, I think, the 3 most useful and probably popular approaches. The last of those approaches is called multiple imputation, which is probably the most widely used. And we'll talk about how we use multiple imputation and combine it with statistical models. And assuming there's time, I'll talk about a little example that I've published a few years ago. So what are missing data? Well, it's pretty much exactly like you would expect. If you have observations of data, say persons, and you are observing many variables from each person, then missing data is when any one of those variables is missing a value. This often occurs from mistakes with manual data entry, and it can happen from automatic data storage making mistakes or just incorrect measurements. In longitudinal studies, it often comes about from either dropout or death of the participant. And it turns out that if the reason they drop out or die along the way is correlated with the thing being measured, then that can be problematic. Why is missing data a problem? Well, usually what we're doing when we analyze data is we're modeling some outcome, and we're trying to draw inference regarding the association of an explanatory variable on that outcome. The model estimates the coefficients or the point estimates of that association, and these may be biased if the missing data is missing due to certain reasons and certain amounts of missingness. So we have to think about both what's the nature of the missingness as well as how much of it is there. The missingness can potentially bias the model's estimate, the point estimate, as well as the standard errors. And it's easy to see how losing data can reduce your power to detect associations. Here's a little figure of statistical inference. This large green box here, we consider the population, and there are unknown parameters that describe that population. We can usually not get our arms around an entire population, so we gather samples, and from those samples, which we usually want to be random samples that they're representative, we calculate sample statistics, and from those sample statistics, we make guesses about the whole population. That's the process of statistical inference. Very simply, missing data can reduce the representativeness of the sample and therefore distort the inference that we want to draw about the population. Another way to say this is if your sample is biased because the missing data is not completely randomly the same as what you have, your inference may not be accurate or reliable. So some of the problems created by missing data, there's the loss of power. It can really complicate your analysis, and it can result in biases in the associations that you're estimating because of the differences between the missing and the complete data. So if we want to do something about missing data, we start off thinking, what would be the most important characteristics of an approach to deal with missing data? First of all, we would want to use all the information that we can get out of the data at hand. We would also want to minimize the bias of these estimated associations. Again, I'm talking about the associations of some explanatory variable with an outcome in an analytic or statistical model. We would also want good estimates of uncertainty, such as the standard errors of those estimated associations and statistics that we construct from them, from which we calculate p-values. Way back in 1976, Don Rubin, who was then working, I think, for the Educational Testing Services, the folks who administer the SAT, he provided a framework to think about missing data. And the key to this framework is to think about what is the missing data mechanism. The missing data mechanism is simply what is the thing that's causing a variable to be missing a certain value. And in order to help develop a framework, he introduced several classes of missing data whose nature is largely determined by their missing data mechanism. This was the paper in 1976, Inference in Missing Data. And this really started a revolution in how we were able to work with missing data. The first class that Rubin defined was called missing completely at random, or MCAR. And values in a data set can be missing completely at random if the events that lead to missingness are independent or unrelated to either observable or unobservable parameters of interest. This is the ideal situation for missing data. And if you somehow knew that your data truly was missing completely at random, then a lot of your worries are already resolved, except for the loss of power, because you would still lose information from missing observations. The other point is that even though there is a formal statistical test for missing completely at random, it's not used very often. Most of the times people are going to want to work with our next class of variables, next class of missingness defined by Rubin, which is called missing at random. Missing at random is a weaker assumption than MCAR. And very simply, it means the missingness, the reason that a variable is missing a value is not at all related to the value of the variable, okay? This cannot be tested formally. This is part of what's so maddening about missing data is it's this very elegant theory and it has all this utility, but a lot of it cannot be directly tested. Missing at random in the literature is often used interchangeably with the term ignorable, although to the purists, ignorable really is meant to describe the missing data mechanism that results in data that is missing at random. So just a little terminology there that you see. If missing data are missing at random, this relieves us of something that's very burdensome and difficult, which is we don't need to model the missing data mechanism. This is really the key underlying assumption for the most important missing data methods. If you simply ignore missing data that is missing at random, your results may be biased. What are some examples? Well, accidentally omitting an answer on a questionnaire, a fire drill interrupts something. In one study I'm working on with colleagues from Penn State and USC, we actually lost follow-up because of the pandemic. You remember when folks weren't allowed to come in person, different places. So the point there is that the reason they're missing data is not at all related to the values that would be recorded. Here's a little slide just to remind us that usually we're modeling an outcome and we're interested in its association from an exposure after adjustment for confounders, which we also call covariates, okay? Now, it's the association between the exposure and the outcome that missing data can bias. And so this is what we call the analytic model, and this is what we get our results from our study for. In a little while, we're going to see that when we use a technique called multiple imputation, there's another model we have to think about. Let me advance. So the last class of missing data that Ruben defined was missing not at random. Now, in the literature, this is sometimes spelled as NMAR, but more recently, this spelling has become popular. But if you see any papers with those first two letters reversed, it's the same concept. This is data that is missing because of the value of the variable that would be reported or measured. Very common in income data, there's missingness because people at the high and low ends of the spectrum generally don't feel comfortable, or sometimes don't feel comfortable reporting. So you see there that the mechanism that's causing the missingness is directly tied to the value that might be reported. This is true sometimes with disease status and also with, say, history of incarceration. People sometimes won't fill that out on a job application because they hope the reviewer doesn't see it, because if they ask them, then they have to tell them the truth. And if you have a long history of jail time, it might ruin your shot at employment. Just like other types of missing data, though, if the missing data is missing not at random and you ignore it, your results can be biased. Now, later on, we'll see that if your missing data is missing not at random and you want to rigorously address it, then you need detailed knowledge regarding the missing data mechanism. And further, you must jointly model the model of the missing data mechanism along with the analytic model that's in your subject area. You must be forewarned that the data, by its very nature, does not contain any information about the missing data mechanism. So it means you have to have expert prior knowledge on the missing data mechanism in order to model it from sources outside of your regular data. Okay, so we've talked about these three important classes of missingness: missing completely at random, missing not at random. Now we're going to talk about three approaches for dealing with missing data. The first is called complete case analysis, or synonymously listwise deletion. The second is called maximum likelihood estimation. And the third type is called multiple imputation. We note that the latter two approaches assume that the missingness is missing at random, okay? So listwise deletion, complete case analysis, is very simple. So again, going back to this example I mentioned earlier, where persons are your analytical units, and if you're measuring 10 variables on each person, with listwise deletion, any person that's missing any value of any of the variables is just tossed, okay? So it's very simple. This is quite commonly used, and what may be one of the few surprises in this talk is that it's fairly benign in many circumstances. So complete case analysis is not automatically a bad thing. Now, one serious disadvantage is it may lead to a large loss of power. It also does not use all the information available. If it turns out the missing data is MCAR, it does not introduce bias. If the missing data is missing at random, it may introduce bias. In general, it yields pretty good standard errors. And something I learned recently, which to me was quite surprising, it's quite robust to missing not at random among explanatory variables, not in the outcomes, but in explanatory variables. Again, I'm throwing a lot of stuff at you, which is a little bit abstract, especially the first time you hear it. So to drive home that last point, let's imagine you want to model the number of car accidents per year as a function of the income of the drivers. Well, we've already said missing income data that is missing is often missing not at random. It can be substantial. In my mind, substantial is greater than 10%. If you use only those observations that have income data, right? This is complete case analysis. It turns out that modeling the number of car accidents on income will yield an unbiased regression coefficient for income, okay? So that's what that last point about listwise deletion meant. The second technique we'll talk about is maximum likelihood. Now, you've likely heard of this expression before because maximum likelihood estimation was developed by Sir Ronald Fisher in the last century and is kind of the workhorse of modern statistical analysis. What it does is it chooses parameter estimates, again, going back to our idea of we're modeling the association of an explanatory variable on an outcome. It chooses the parameter or the model estimate that maximizes the probability of observing the data that you have in hand. These estimates have great properties. That's why we use them. They are consistent, meaning that they are unbiased in large samples. Asymptotically is a $10 word for very large samples. They are asymptotically efficient, meaning they have minimal variance with high sample sizes, and they are asymptotically normal. These are all highly desired properties in statistical analysis. If you're using maximum likelihood to address missing data, you generally assume multivariate normality of all the variables that you're considering. You assume that the missingness is missing at random, and you have a number of options for how to implement. The simplest way conceptually is to factor the likelihood for a monotone missing data pattern. That's a missing data pattern, which is rare. It's elegant and simple in that you're missing in one variable and then you're missing in two variables next to each other and three variables. Rubin also came up with an approach called the expectation maximization algorithm, which can perform maximum likelihood. It doesn't yield great estimates of standard error, so you can use bootstrapping for that purpose. The most common way that maximum likelihood is used to address missingness is with direct maximization of the likelihood. Now, this is also known as full information maximum likelihood or raw maximum likelihood. Different fields tend to use some of these statistical terms different ways. What it does is it directly maximizes the likelihood of the outcome for the model of interest, okay? It yields unbiased estimates of the standard errors, and This has been around for a long time in structural equation modeling packages. Now, biostatisticians have kind of a complicated relationship with structural equation modeling. Some of us use it, some of us hate it. Some of us use it with caution. I'm probably in that last group. Some stats packages like M+ is the Cadillac for structural equation modeling. That can do a lot with direct maximum likelihood. Stata can do quite a bit. SAS has a proc called KLIS, which can do a fair bit also. The way maximum likelihood works is, unlike multiple imputations, which generates multiple copies of the data, it kind of works under the hood. If the data is missing for a given observation, the software doesn't throw out the whole observation, like in complete case. What it does is it works around the missing values of specific variables by integrating the likelihood over those variables with missing data. So this allows it to use all the available information, which you may recall we said was one of the criteria that we'd like to see in any approach that rigorously addresses missing data. So proc-KLIS in SAS does full information maximum likelihood for a wide class of linear models with latent variables. So latent variables is something that's part and parcel of structural equation modeling and very much the bread and butter of psychologists and social scientists. Now, direct maximum likelihood, I was talking a little about this package called M+. M+ can do full information maximum likelihood for both explanatory and dependent variables outcomes for many types of regression. So logistic, Poisson, negative binomial, Cox. M+ even has some capability to handle missing not at random. Okay, turns out SAS does also. Okay, so that's, but this is really makes M+ so attractive to people in structural equation modeling, but also those of us. The beauty of maximum likelihood is you don't have to create multiple data sets. The same time it's estimating your model, it's working under the scenes to deal with the missingness in a very mathematically appropriate way. So now the good news for those of us who use SAS, which is quite a few of us here at Penn State and in many institutions, especially where you analyze randomized controlled trial data, is that if you model your outcome with proc-mixed or proc-glimix, it turns out that both of these procs, now proc-mixed and proc-glimix. Proc-mixed is a function in SAS. It's for linear regression where you want to include random effects and or direct modeling of the correlation of errors. Proc-glimix expands that to this wider class of models called generalized linear models. Both of these procedures in the major functions in SAS are called procs. That means it's short for procedure. Both procedures implicitly apply maximum likelihood with an assumption of missing at random on the response variable. So this is kind of a great shortcut. You do have to have either random intercepts or correlated errors in your model. When SAS does this, it appears on the output like it's deleted the whole observation, but it hasn't. It's working around the missingness to use all the information. One important caveat is that neither of these procedures in SAS handle missingness on explanatory variables. So if your missingness is only in your outcomes, then proc-mixed, proc-glimics are a very elegant and easy to use way to address that missingness, okay? But they don't work if you're missing in the explanatory variables. So just to review maximum likelihood, it uses all the available data. It minimizes bias if we have reason to believe that the missingness is truly missing at random. It provides good estimates of uncertainty. Software can be iffy. It's not in all software everywhere all the time. It's a very solid alternative for missing data in clinical trials, especially missing data in the responses. And unlike multiple imputation, which we're about to start addressing, it doesn't involve a second model that generates missing data. So there's no need to have to worry, does my analytic model, does it agree? Does it comply and play nicely with the imputation model that's used in multiple imputation? Here's a paper I recently found very good. Ian White, he's from England, writes very well about missing data. This is a nice paper talking about, should multiple imputation be the method of choice for missing data in randomized trials? And they essentially conclude that you may not have to do multiple imputation, especially if most of your missingness is in the outcomes and you use one of these random effects models. So let's switch now to imputation. Historically, folks would use single imputation, and this is not a good practice because they would take all the missing data for a certain variable and say, put in the mean or a conditional mean, or they'd use an approach called hot deck. A big part of this is that you're just filling in a missing data with a value, and then you're pretending there's no uncertainty with that process of generating that imputed value. So single imputation is not a good way to go. And it turns out that multiple imputation fixes nearly all the problems or challenges with single imputation. How does it do this? Well, it constructs a new statistical model to estimate the missing values under an assumption of missing at random. So multiple imputation has a model that's generating the missing values, okay? What it does is it generates multiple sets of the data, and in each set of this data now, you can have different values that were originally missing. And it turns out that you will fit a model to each of these data sets, and you will generate a set of coefficients, and then you will have to combine them. This was also introduced by Don Rubin in this classic textbook in 1987 called Multiple Imputation for Non-Response in Surveys. And again, it's a foundational text. Here's a little image. So you have your original data with missingness in different variables. With multiple imputation, you generate multiple copies of that data. But the value that's filled in for the missing value can be different in every one of these different copies because it's being drawn from a multivariate joint distribution. And so this is a good thing because it allows us to rigorously account for the uncertainty injected into the imputation process by the imputation model. Multiple imputation, when it's done correctly, it produces estimates for an analytic model that are consistent and asymptotically efficient and normal. We saw those terms before for maximum likelihood. Unlike maximum likelihood, it can be done with almost any conventional stats software for nearly any kind of model. It also uses all the available information. And again, when properly implemented, it minimizes bias and yields good estimates of standard error and uncertainty. So remember, these latter things enable a proper statistical testing of our results with p-values. So an imputation model is used to replace missing data, while an analytic model is used to analyze the data after imputation. Now, the real key here is that because the results of your analytic model, their validity, their worth, are really contingent upon the comprehensiveness of the data and therefore the sophistication of the imputation model. Just to give you an example of what this means, if your final analytic model has an interaction in it, then you'd best have that interaction as part of your imputation model. Otherwise, the data generated by this imputation model is not complex enough to accurately represent what's going on in the interaction that you use in your analytic model. So going back to this slide we've seen a few times, we're modeling the association of an exposure on an outcome, and we're including adjustment for confounding variables. And but when you use multiply imputed data, you're using a completely separate model called an imputation model that's filling in the missing values. And that imputation model has to play nicely with the analytic model. So what are some of the imputations of multiple imputation? Its implementation can be complex. If you're using different analytic models, you may have to generate different sets of imputed data. It directly uses statistical models to fill in missing values, unlike maximum likelihood. And to avoid bias in the estimated associations, the imputation model must be compatible with the analytic model. And what does that mean? It means that the imputation model should be as complex or more complex than the analytic model, so that the data generated by the imputation model has enough granularity, rich information to fully inform the analytic model. There are two popular algorithms for multiple imputation. The first is called the Markov chain Monte Carlo. It's also very well known to those of you familiar with Bayesian statistical analysis. This is the most widely used algorithm, and it's the default in SAS's procedure, PROC-MI. The second approach is called fully conditional specification, but commonly goes by two other names. One is MICE, multiple imputation by chained equations. It's also called sequential generalized regression. We'll talk very briefly about MCMC. This is an algorithm that is the workhorse of Bayesian modeling. In its use in missing data, it postulates a joint distribution of all variables, usually multivariate normal. It can also do that for multinomial, which is a multivariate distribution of categorical variables. It converges to the correct joint posterior distribution, and it is readily available in these common stats packages. Here's some SAS code that shows you how simple the code can be to run this. The top little block is the multiple imputation procedure, PROC-MI. You have input data, you give the name to an output data. All the variables here, because we're not stating any algorithm, it's assuming the default, which is the MCMC. It's going to assume that all these variables, whether they're continuous or categorical, that they all follow an underlying multivariate normal distribution. PROC-REG fits linear regression to, now your input data is the output data that contains the multiple copies of imputed data. you output the estimates from this data, and you output the covariance matrix, and you fit the model separately to each imputed data set. That's what this by imputation means. And then proc-MI-analyze uses Rubin's rules to combine the different sets of estimated coefficients and combine them into one kind of global set of coefficients. So that's how simple the code is. Of course, with almost all statistics, the real challenge is understanding what the code is doing and what's going on. Now, Rubin's student, Dr. Joseph Schaefer, is arguably the most famous statistician at Penn State because he developed the MC-MC algorithm building off Rubin's work. And it is really Schaefer's work that is implemented in SAS, proc MC-MC. This was his textbook in 1997. Now, the other algorithmic approach is called fully conditional specification. This does not assume a broad overall multivariate distribution for all the variables. Rather, it allows you to pick a separate model for each variable that has missing data. Mathematically, it is not guaranteed to converge. So it does not have the elegance of the MC-MC algorithm or maximum likelihood. It is widely available. Even though it has not been shown rigorously to converge, simulation results are very encouraging, and this is widely used. So it's very popular. It allows you to pick a couple different options when you're imputing continuous variables. You can do predictive mean matching or linear models. For categorical variables, you can do logistic and a discriminant analysis. And you can use Poisson. SAS only has Poisson. It doesn't have the negative binomial, but some other packages do. And here's the SAS code for the FCS approach. Notice you have a line of code that says FCS, and you're saying for these two categorical variables, I'm going to model each of these as a logistic binary outcome. And for self-efficacy, I'm going to model that using regression based on predictive mean matching. And for race, which is multi-level, I'm going to use discriminant analysis. Again, you generate the imputed data, you fit a model to it separately to each imputation, and then in this last little block of code, you combine the different sets of estimated associations to come up with a global solution. Now, concerns with multiple imputation, you want to make sure that the imputation model is at least as complex as your analytic model. Vice versa does not have to be true. Different analytic models may require different imputation. And if you're using longitudinal or clustered data, there are some very nice ways to use it, but we don't have time for that today here. Now, I thought I'd check in with folks. Normally, when you give a talk, I've given a couple talks over the years on missing data, there are usually a zillion questions. So I don't know if it's better for this group that we just start using our remaining time to answer questions, or if I talk through a very kind of simple example to show how I've used this. Here's a summary. Listwise deletion is the lesser evil of conventional methods and can actually work out surprisingly well. Maximum likelihood and multiple imputation, these are really the go-to methods of dealing with missing data. And I'll say one last thing, which is it's been more and more the case that in our table 1 of clinical journal publications, we need to really describe the missingness accurately so that people can really take that into account when they're interpreting the results of any analysis. I don't know, let's open it up for questions and I'll stop sharing. I think there was one question in the chat. Let's see. Oh, okay, that had to do with the full screen. I know it's always uncomfortable. Anyone want to ask questions, or would you rather I jump into a simple example?
Yeah, for our attendees, if you have any questions, please feel free to ask. Yeah.
Yes, this is Jason Liao. So I thank you for a very good talk. In fact, I learned quite a few things. So one thing I've been thinking about is this multiple imputation. So seems it serves three roles. Yeah. So the first is to make the computation possible. So in the old days, if you do not have regular data, and a lot of software packages simply does not work. So then by imputation, you make the data set regular. So you can do that. So that's first rule. Second rule seems that it's just to avoid the bias when you have missing data. Okay, so that's the third one. A lot of physicians, they seem to think, okay, I have missing values on these outcome variables, right? For some subjects, no worry. You just do multiple imputation and you fill them out. So to them, this multiple imputation is a way to generate the missing information. So I have always been highly uh, doubtful about the third, like you can just use multiple imputation to fill out the information, unless you really can generate a very good model. But the way you talk about the MLE approach, so you basically model the missing value for that specific observation for specific subject. So you don't need to worry about like the first approach. You need to get a rectangular like data set. So I think it all makes sense. So I would like to see what you think about these things.
So just so folks know, Dr. Liang is a professor of biostatistics who does a lot of work in the Cancer Institute. So I would say that people who really study missing data methods, they tend to gravitate toward the maximum likelihood because one, it avoids all the complications of generating these multiple data sets, and it completely sidesteps the necessity of an imputation model. So as Jason is saying, he's questioning, well, how good is your imputation model? For instance, I really do not like to ever impute race because I don't think that we can capture enough good variables to really do a good job of filling in race. So in my statistical practice, I generally never impute race because I just don't think we can do a good job with it. I don't think we measure variables that could really allow us to do a great job modeling that. And so in that sense, I share Jason's concern there, okay? But many people will go ahead and they'll apply it to anything. And in my view, a big part of the responsible use of missing data is choosing a broader set of explanatory variables from which you really can make a case that it's plausible, that there's enough information in this set of other variables that it's very reasonable to use a statistical model to fill in what's missing. I generally talk that over with the physicians or the clinical investigators. And if they don't feel confident or comfortable, then I would never foist an imputation model on them. So just in short, maximum likelihood in some ways is the ideal, but it's really limited to the outcomes, and it's often not quite as easy to get the software for. Anyone else? What about, so Jason, you know, a veteran statistician, has a lot of experience in thinking about this. Any newcomers want to ask anything?
Harry, there's one comment in the chat box. I think
Sure.
people
Okay.
want to see some examples.
Sure. Let me show you one example. Anyway, here's my last slide. And we can do lots of stuff. The techniques that I'm describing are very sophisticated. They are very rigorously supported by mathematical proofs, by simulation. But the single best way to avoid headaches with missing data is to avoid it altogether, to structure your data to prevent it in the first place. Okay, I would be remiss if I didn't throw that in. Okay, let me show you an example real quick. A paper that we published in the Journal of the American Geriatric Society in 2019. I was first author of this paper. I was using imputation for sensitivity testing of the competing risk of death. I had a cohort of 754 persons who were all 70 or older at the start. We followed them on a monthly basis for over 23 years. Clearly, over this time, most folks died. And it turns out that when you're following them longitudinally, death is often correlated with the bad outcomes that you're studying. In this case, we were studying fall-related hospitalization. So you fall, you're injured seriously enough that you go to the hospital. We had just shy of 4,000 person intervals. A person interval was an 18-month period. At the beginning of each 18 months, we would measure all the covariates, and on a monthly basis, we would measure the outcomes. So we had greater than 10 years of follow-up. I didn't use all 23 years. I used like the first 12 years of the data. Over this period, 63% of the persons died in our study. What I'm going to focus on here is the association of an explanatory variable, which is 3-level body mass index, specifically indicators of being overweight or obese relative to a reference group, which was normal or underweight. It turns out that if you model fall-related hospitalization, being either overweight or obese, both of those are associated with the occurrence of fall-related hospitalization, but surprisingly, they are both mildly protective. I say surprisingly if you're not in the aging research literature. If you're in the aging research literature, you've heard this so many times, you're no longer surprised, right? And why is that? Well, the simple explanation is bone mineral density. Folks who are heavier have, on average, higher bone mineral density, and this protects them somewhat. Now, it protects them somewhat from falls, but it does not protect them from death. In fact, we know that both of these things are associated with higher rates of cancer, heart disease, et cetera. So here's my complete case data. And by complete case, what I mean is, as soon as the person died, I just stopped their follow-up, right? If I keep them alive to the end of follow-up and I use a imputation model, assuming missing at random, to fill in whether they had the outcome or not, I get very similar results to the complete case. If I assume that after they die, well, they're dead, so they can't have the outcome anymore. If I keep them alive artificially, if I keep them in the data set, I pretend they didn't die and I keep them in the data set, but I assign everyone a 0 outcome, it turns out that the associations of both obese and overweight lose their statistical significance. Why is this? We believe this is because people are dying because of the obese and the overweight associations. So they're dying for these reasons before they actually have the fall-related hospitalization. If, on the other hand, I take all the decedents and I say, yes, let's pretend that all of you had the outcome, I get results again whose point estimates are very close to the complete case data. And the confidence intervals are compressed quite a bit because I have many, many more outcome events that I'm modeling. So anyway, I'm so sorry. I was not sharing the image, right?
Yeah, sorry.
All right, so here's the complete case where both overweight and obese are protective against fall-related hospitalization. This is slow gait, which is, it's a measure of frailty, and it's always positively associated with every bad outcome that happens to older folks. If I impute using MAR, I keep people in the data set after their death, and I impute their outcome, whether they had the hospitalization or not, the results are nearly identical to complete case. If I keep the decedents in the data set beyond their death, and I don't allow any of them to have the outcome, that model, the model of that data now eliminates the statistical significance of being overweight or obese. If I allow all the decedents to counterfactually have the outcome, again, I get point estimates that are very close to the complete case data. I like this example because in many ways, multiple imputation, apart from boosting your power and allowing you to do more things, it allows you to look at possible counterfactual conditions to see how robust your results are. I'm sorry, Deborah, your voice is breaking up. I can't hear you. Do you want to type in?
I think it's just a noise, Terry.
Oh, okay.
Yeah.
Let's see. So normally, right, you have a study, you're studying some outcome, you want to model it on some exposure, you have covariates. You may be missing data in the outcome, in the exposure, and in the covariates. And in my experience, you probably are missing some in all of those, okay? Multiple imputation, despite its complications and its challenges and its limitations, does allow you in nearly every circumstance to address that missing data. Now, my colleague Jason pointed out a very important caveat, which is you have to have some confidence that you can responsibly model the missing values of all those variables. In my case, I won't do that for race. I won't do it for some temporally very specific things, like in one study, we had a variable chest pain in the week before hospital admission. Well, in my view, because I didn't have many other variables measured in that time frame before admission, I do not think we could responsibly model that. So I pushed back against that. Mind you, this is a very broad brush overview of an area that people have now been working on for nearly 50 years. So there's a whole lot more, but I've tried to give you this gentle introduction, mostly to the conceptual pieces. Okay, so I'm going to read a question on the chat. It says, for large data sets, how would you recommend identifying variables to include in the imputation model? So in imputation, in my experience, it's quite rare that you get in trouble by over-including. So here's what you would do. You would want to take any variables that you think help explain other variables that are missing data. You want to include the outcome, okay? You definitely want to include the outcome of your analytic model. You want to include any interactions that you think you might use in your final model. But basically, you can err on the side of inclusion. Now, I've imputed data sets with several million observations there. I limit it to the covariates, the outcomes, and any other auxiliary variables that I think plausibly inform the missingness of any of my explanatory variables or covariates or the dependent variable. So it's kind of a short answer, but with most reasonably sized data sets, you don't have to worry too much about pruning down the data. But for very large data sets, yes, you do, because it gets unwieldy.
All right. very nice talk, Terry, and very useful too. Any last minute question?
So there was one follow-up question. As a follow-up, if we have different subpopulations of interest, should we impute separately by group? That is the recommendation. So in other words, if you are planning, say you're doing a sex-based analysis where the effect by sex is really important, they recommend you separately impute males from females and then combine them. Okay. And same thing with you know, if you're going to have interactions between sex and other variables, that's another good time to separately impute by sex, because after you combine them, you have already accounted for all the possible interactions with sex among the other variables.
Yeah, I think that's actually a very good question.
Very good question. Thank you so much
Yeah.
for your attention. This is difficult stuff to hear about. It's so abstract, and it's the afternoon, so thank you.
Thank you very much, Terry. Yeah, nice talk. Thank you, everyone. See you in 2 weeks.